Hello again, future engineers. I thought it would be a good idea just to let you see some of the components that you will probably end up using to make this little circuit. The circuit itself is going to be in a packet. You will be supplied with a printed circuit board that may look something like that. See these copper tracks on there, those lines in the spots, they are called tracks and pads. The tracks connect components together, and the pads are where you solder the leads of the components to. But you will put the components on this side and the soldering on that side. You'll see that there are little clear spots. You'll drill those out. But to be honest, I think the ones that you'll get will actually have pre-drilled holes and everything. So it won't look like this, but this is an example of a PCB, a printed circuit board. So, the most common semiconductor device is the one that's just in front of the camera just now. And this is a resistor. Excuse me. The camera is not that great at picking up things so small. I mean, there's my thumb as an example of the size of this. But that tiny little object there is a carbon film resistor. And what its job is to do is to limit the amount of current that can flow into a particular part of your circuit that you design. They're very light, and you might be able to see that there are stripes on them. There's usually 3 bands that are coloured, and you probably won't see the one on the end. It's a metallic looking colour. I'll do a video on what these mean, but essentially it's a kind of way by which we can tell which resistor has what value of resistance. This is the body of the resistor, and these are what you call the leads. So they're the bits that you solder. These are metal. So there's actually like a little carbon film in there that judges how much current it allows past. You know, gives it its different value. The one that I'm just putting in front of you now, oh, this is a 1 ohm resistor. 1 ohms. Here is a 1 million ohm resistor. They're exactly the same size, but the million ohm resistor will offer 1 million ohms of resistance. So it'll make any current that can pass through it, will be reduced greatly. It has stripes too. Now sometimes you don't want just a fixed value of resistance. You need to be able to alter it and tune it. In that case, we have a thing called a preset variable resistor. So on the top here, you might not see it. See that tiny little groove in the center? I'll poke at it with a lead. It's just there. That's actually a hole for a screwdriver, and you can twist the center of that device around and it'll give you different resistances. If it's fully one direction, we'll say clockwise or anti-clockwise, it has a value of very low resistance, if not zero resistance. But when you twist the center all the way around, you get a high resistance. It's got 3 pins, this one. Yep. Maybe you don't want a preset resistor, you want one that you can actually adjust on the outside of a piece of kit, like a dial. In that case, we might use a potentiometer. It's a much bigger piece of kit, but it's exactly the same as the thing I just showed you. It's got the 3 tabs and a dial which we can attach a knob to, and then we can twist that around and get the value of resistance that we want. These are easier to use. Usually there's something stamped on the bottom, and this is a 25,000 ohm resistor. I don't know if you'll see that in the camera. If I get really close, you might. See the 25K and the symbol for ohms, omega? 25,000 ohm resistor. So this will give you any resistance you like between 0 ohms, 25,000 ohms. We use these for directing signals places as well, but you may have seen them as like a volume knob in an old stereo, really old stereo. Now here's an example of a 10,000 ohm resistor. You see it's a bit more chunky when you compare it to the quarter watt one. This is a 1 watt resistor. The one at the back here is a quarter of a watt. This just means this can handle more power. So if your system that you're designing has naturally higher voltages and naturally higher currents, you need a component that can withstand those type of situations. So this one's a bit more beefier, a bit chunkier, a bit more robust, 1 watts. But again, the amount of resistance it has is worked out when you look at the bands that's on it, the different coloured bands, which again I appreciate you can't see. Those are resistors. So that's one part of a circuit, and they exist in pretty much every single circuit. The other thing I want you to see is a 2200 Farad capacitor, if I can get it to sit still. Now, capacitors come in lots of different shapes and sizes. I've picked this one simply because it is fairly huge. It's a big capacitor. It holds charge, okay, and the amount it can hold is measured in farads. Okay, so farad is the unit of capacity, if you like, its ability to store charge. Not so much the amount of charge it can hold, but its ability to store that charge. So that's measured in farads. This one is 2200 microfarads. Okay, so we're talking much less than 1 farad. This one is radial. It has no, it's not, it's axial. It's kind of like got an axle that goes through it. Okay, its leads are on each end, like the axle of a car. Inside there is a great big roll of film. I'll probably do a video that explains exactly how all these components works, but I just want you to be able to see them at the moment. So this one, you have to put it in the correct orientation. See the arrow? So the arrow has to be facing the direction of the flow of current. If you put it in the other way round, it can heat up and explode. And a big one like this could go off with quite a bit of a pop. So I'll let you see some other capacitors, just to let you see that they are all completely different. Here we have the same type of capacitor. It's an electrolytic capacitor. The last one was electrolytic as well. You can tell them because they do have that funny little can shape with the kind of groove around the edge. This is a thin part that can expand and take a bit of pressure if you plug it in the wrong way around. Here's another one, exactly the same type, but they both have slightly different capacities. This one is, if I can see, the writing's really small. This is a 10 microfarad capacitor, the one in my hand, and this one is, it's all written on the can on these ones, they're really easy to read if you've got the eyesight. This is a 22 microfarad capacitor. It's rated for 63 volts, and this one is rated for 100 volts, I think. Is it? Looks like it. Yes, 100 volts. So, if you've got a circuit that requires a voltage of 100 volts, and you need to store some charge, then you need something that's rated probably even higher than this in voltage terms. You always add a little bit on for extra, just insurance. So what do capacitors do? Well, they can be used to slowly let an LED light up really slowly, or let it cool down really slowly. They're used in timing circuits, and it's just because they take a certain amount of time to allow a particular voltage that you've designed in your circuit to be passed on to the next stage in the circuit. So they can be used to like soften things like LEDs. I'll show you an LED when we get that far round. Let's have a look at another couple of types of capacitor. Here we've got a polystyrene capacitor. It's the exact same job it does, but it's just a different type of capacitor. It's just made in a different way. So this one, you tell me, is it axial or radial? It is axial. And these ones, I don't know if I'd mentioned it, the ones with the two legs coming out one end, these are radial, because it comes out of the radius of the bottom in that orientation. So, polystyrene, electrolytic, they're all electrolytics. Let's have a look at another one. This is a polyester capacitor. These are more hard to read. They have some writing on the top. It's very difficult to read, it's embossed. And there's a code. So you need to know how to work the code to work out the capacitance of this particular type of capacitor. We may do a lesson on that, but I think for your course you'll probably be given the right size capacitors. This one can go in any way round. Okay? So it doesn't matter whether you plug it with this lead going to the negative or the other lead going to the positive. It doesn't matter. Here is a dipped polyester capacitor. The same again. There may be some numbers on the other side if we turn it over, or maybe not. Oh, there's something written on the top, but there's no way you're going to see it without a magnifying glass. I can't see it either. I find oftentimes the best way is to look at the tub it came out of and check the data sheet and just make sure that way. If your eyesight's poor, what can you do? Another two examples of capacitors. So the one in my hand that I'm just about to put down is a Tantalum bead capacitor, and this one over here is a ceramic capacitor. Again, don't let the size fool you. It doesn't really matter. They can, well, I can't see what's written on that. Nah, it's too small to read. But for certain applications you may find that some of these are better than others. You know, the polystyrene one here, the polystyrene ones are good in circuits like radios and things where you have rapidly changing signals. You know, the big guys here may be used in power supplies where it doesn't matter how quickly the power is altered, you know, the voltage, you know, rectification and stuff like that. So maybe you'd use this as a clamping capacitor for higher voltages, you know. Let's see what the voltage rating is on this one, incidentally. Well, that's quite disappointing. It's only rated for 25 volts, this one. So, again, you know, it depends on the size of these things and what you're using them for. But as you go through this, and if you really get into it, eventually you'll learn which capacitors are the best to use in which situations. But they store charge. Now, this device is probably the most important electronics device that was ever created. This is a I'm getting a phone call at the same time. This is probably the most interesting and important electronics device that was ever created. It is a transistor. That's the word I'm looking for. I'll show you another one. They come in different packets. This one has a can. So you see that it has a metal can on the top and 3 leads that come out the bottom. The leads are important. They have special names. We call them a base, a collector, and emitter. So that's base, collector, and emitter. All of these type of transistors have these legs with these names. And there's another type. These are bipolar junction transistors. There's another type called a field effect transistor, and they have slightly different names. I think it's called a gate, a source, and a drain. But what do these do? Well, you can use them as little switches. You can use them in amplification. You can use them to design and create logic chips. And logic chips are the precursors to all the clever technology that you have inside your mobile phone today. Without the invention of these, nothing really technology-wise would really exist today as we know it. These is probably the single most important invention of the 20th century. So how do they work? Well, this is a PNP bipolar junction transistor. It has a base leg, a collector leg, and an emitter. And if you apply a little bit of current to the base leg, it allows some current to flow from the collector to the emitter. Simple as that. But the possibilities of the things that you can design using these alone, and a handful of the other components I've just shown you, is immense. So they both do the same kind of job, but as I say, you can use them in switching, you can use them in amplification. They're a fantastic little device. You can control larger currents with tiny little currents, like a signal. That's how you can amplify a signal. So, important things. Couple more things I want to introduce you to. This looks like a resistor, but it's not. This is a thing called a diode. Again, they come in different size packages. They're rated for different applications voltage wise. So the one in front of you here, the black one, I don't know if you can see a tiny little stripe on one side of it. Okay, on this side here. That tells you that this device needs to go in a certain orientation, kind of like those electrolytic capacitors I showed you. Diodes are clever because they allow electricity to flow in one direction, say from here to here, but they won't allow it to flow in the opposite direction. So in this direction from here to here. Now that is really, really useful for building circuits. What's the use of a diode? We use diodes in rectifiers, so you might know that the electricity that you get from your wall socket is an AC electricity, alternating current, which means it goes back and forward all the time. And things like your GoPro and your mobile phone and your, well, anything else that's the inside of your computer, your desktop, all that technology uses direct current, which means electricity that only flows in one direction. So we can use diodes like this to change AC current or AC electricity into DC electricity. So as I said, they come in different shapes and sizes. So this one is a special type of diode called a Zener diode. and it's used in voltage stabilization and to make sure that your power supply that you've designed doesn't end up delivering too many volts to your circuit, or not delivering, but placing too much of a voltage across your circuit. So, regular diode, Zener diode. There's lots of different types. Here's one you probably will be familiar with. Oh, these are both axial, by the way. This, take these out of the way, is a light emitting diode. This one happens to be green, and I think you know what they do. Again, they have to be set up so that the current travels through them in the correct direction. So you might notice that one leg on this, round this side, that leg is actually longer than this leg. And on some of these you get, well, the long leg's the positive leg. Sometimes the actual body of the light emitting diode has a wee flat edge. The leg that sits next to that is usually the negative leg. So if you know what you're looking at, it's easy to figure out what way round to put this. But if you don't know, there's data sheets for all of these. Every single component has a data sheet which you can look up online. So if you pass a current through this tiny wee current, you'll get a nice bright green light. Normally, a diode, a light emitting diode, needs to be protected, by a resistor. So you might have a circuit that looks something like that, with a resistor either in front of or behind the LED, and that just limits the current going into the LED and stops excessive current from damaging it, keeps it working. See if there's any remaining things. Oh, there are. One of the things you're definitely going to use is an IC. So the IC stands for integrated circuit. It is a chip. And believe it or not, inside this particular chip, which is a 555 timer chip, there are hundreds of these and hundreds of these and possibly a couple of these. But look how much smaller the chip is in comparison to the passive components that you could use to replicate this chip. You could build that chip using all the things that I've shown you so far, but look how small the chip is. And this is a really, it's a useful wee chip. We're going to use it. It's going to control how your lights on your little circuit flash, what speed and what rate they flash at. So we're going to use it for that. It is a timer chip. But look how small it is in comparison to all the other bits and pieces. If you think that there's maybe, I don't know, maybe it could be up to 50, 60 transistors maybe, you know, maybe I was exaggerating when I said hundreds. But there's going to be a lot of transistors going on in there, diodes, maybe a resistor or two just to protect the chip itself. So this has pins. Okay, we don't really say leads, we say pins. And you can see that it's got 8. And they're numbered 1 to 8. And if you look very closely at the top, I don't know if you can see it, if there's enough light, I get close enough.